What do you think? Does this graph represent a function? I'm going to say no, because I'm going to apply the vertical line test, and the vertical line test says if anywhere in the graph you can pass a vertical line through the graph, if it hits it more than one place, it is not a function. And this vertical line hits the graph in two places, right here and right here. So this is not a function, because suppose I was to pick f of, well, that looks like a -3. What value do I get back out? Do I get that y value or that y value? It's ambiguous. I don't know. So for one input, I get more than one output. That's the vertical line test. If a vertical line intercepts a graph, a curve, in more than one place, it's not a function. So we will mark down no, this is not a function. Now what about this graph in number 10? Is this curve here, does this represent a function? Well, if I apply the vertical line test, no matter where I pass a vertical line, here or anywhere, it intercepts the curve in only one spot, right? Only one point. Now this point here is interesting, but look what happens. Right here, when x is that value there, y is that value. The open circle means that that point right there is not included. So by the vertical line test, I'm going to say that this is a function. And another way to tell when you look at these curves is this. Let me get rid of some of that stuff here. When you look at a curve, if you trace it from left to right, if it always goes up or down, it's going to be a function. If it comes back on itself, this is when you have to be concerned. If the curve comes back on itself like this, if it did this, okay, up, down, but if it came back on itself horizontally, then it's not a function, because then you would get the vertical line crossing in more than one point. But as long as you're going in one direction, okay, I'm always going to the right. I'm always moving to the right. So as long as I always move to the right, it's going to be a function. In number 11, we want to find the domain of this function. Now the domain, this is the set of input values that will make this computable. So what values could we put in for x that will actually make this computable? So a good way to look at this is, are there any think of the opposite. Are there any values of x that will make this uncomputable? So think of any number. Can you multiply it by 7? Yeah. Can you add 9 to that? Yes. There's no number that makes this thing incomputable, uncomputable, undefined. So I'm going to say that the domain is a set of all real numbers. Now, I could write all real numbers, or I can do it symbolically by writing this. Or I could write, it goes from -infinity, the x's go from -infinity to +infinity. In 12, we're going to find the domain of this function right here. Now, it's an absolute value function. So what we're looking for are what numbers can we put in here and then substitute in here and compute. And ask yourself the opposite. Are there any numbers that will make 9 minus x undefined? Like, can we not determine what that is? Well, think of any number. Can you subtract it from 9? Sure, no matter what number you think of, you can subtract it from 9. 9 minus whatever number you think of. Now, whatever number you get, can you take the absolute value of it? Sure. All right, so again, I'm going to claim that the result here, the domain, is all real numbers. Every number works, but they're asking us to write this in interval notation. So every number can be found between -infinity and +infinity. Now in 13, what do you think the domain of this one is? Now remember, what we're looking for are all the numbers x that we can put in here and compute. Now there's only one number that we're not going to be able to compute with, right? We get an undefined expression if we divide by 0. So we can't do this, right? You can't have something like this, 5 minus 2 over 0. That's undefined. So every other number will work. Pick any number you can think of. You can raise it to the 4th power. You can divide that into 2 and subtract that number from 5. So everything here works except for 0. Now what we want to do is use interval notation. So I could say all numbers except 0. But if I want to use interval notation, I'm going to write it like this. We can go from negative infinity up to, but not including 0, right? There's the open parentheses. Now, the open parentheses means that all the numbers in here go up to, but do not include the 0. They do not include the 0. All right, so we can get this one. Or, now this here, if you remember, this is the mathematical symbol for or. It's a union sign, right? This right here is equivalent to a union sign. It means union. It means or in English. So we go from negative infinity up to, but not including 0. Or we can go from not including 0 all the way out to positive infinity. So that's our domain. And if you look at it on a number line, it looks like this. All right, here's 0. So you have all of these numbers, and then you have to stop at 0. It doesn't include 0, and then you have all of these numbers. So every number in here is going to work. That means by work, I mean you can put it into here and compute, except 0. Now in 14, what is the domain of this function? What are all the numbers that will make this expression here computable? What can we put in for x to make this thing compute? Well, we got a fraction. The only time in a fraction we have to worry about is what's going to give the denominator 0. So what are you going to put in for x to make this 0? Well, I think it's a 2. So I'm going to say every number except 2. Now, I could write it like this, okay? I could say all x not equal to 2. That's one way to say it, but we want interval notation. So I'm going to go here. Negative infinity all the way up to, but not including 2, or the union sign, starting after 2 all the way to positive infinity. That, I think, is the domain here. Now, number 15, we have the odd root of x plus 15. So we have to know something here. Well, of course we do. What numbers can we put in for x to make this thing computable? Well, I've got a root. I've got a radical here. Now, when I do something like this, if I have a radical and this number up here is odd, okay, like, 3, 5, 7, 9, whatever, if that number's odd, I can put any number in here at all. Any number at all. So in this case, I can put any number in for x. I can add 15 to it, so I get any number back. And then it is okay to take, it's possible to take the odd root of that number. So this works. Right? So this right here is acceptable. That works. And then if I add 2 to it, the whole thing works. Now, the difference is this. If I have a radical and I put, say, an even number here, this number here has to be positive. That one has to be a positive number. So not every number would work. So if you have x plus 15, you have to have that being, well, not even positive. I could say, let me say this again. This could be positive, but a better way of saying it is not negative. I can't put a negative number in here. It has to be greater than or equal to 0. And what's going to make this work? Well, if you subtract the 15, you'll get x is greater than or equal to negative 15. So if we had this, if f of x was equal to, say, the 6th root, right, an even number of x plus 15 plus 2, I would say that the domain then is all x greater than or equal to negative 15. All right, so it works for odd numbers. Any odd number you can put in, any number at all, and that's what we have. So the domain here is all real numbers. So we're going to write that, of course, as this. We're going to go from negative infinity to infinity. In 16, we want to find the domain of this function, and clearly it's a fraction. And the only thing we have to watch out for are zeros in the denominator. So we're going to ask, what is going to make this x squared minus 2x, what's going to make that 0? All right, so we can solve this. It's a quadratic equation. We can solve it. Let's factor out x. So if we factor it, we'll get x, and then what's left? X minus 2 equals 0. And now by the zero factor property, one of these, this one or this one, has to be 0. So I'll write this step. So x has to be 0, or x minus 2 has to be 0. Well, this one's clear. X is 0, or over here, x minus 2, if I add 2 to both sides, x is equal to 2. All right, so these numbers here, 0 and 2, are going to make this expression here, that denominator, 0. So we have to exclude those. Now, if I draw a picture so I can clearly see what's happening, I have to exclude 0, and I have to exclude 2. But I can use any number in here, or any number in here. Now, here's what this is. Numbers in here are going to go from negative infinity up to 0, not including 0, so open parentheses, or, right, there's the union sign, that's an or. In here, we're going to go strictly between 0 and 2, open parentheses, because that means don't include those numbers, or in here. And where are we here? We're going just after 2 all the way to infinity. So there's the domain of that function. And when I see that, right, when you see this, you're thinking, okay, I've got this function right here. I want to compute with it. What numbers can I compute with? I can compute with any number here, or here, or here. But I cannot use 0 or 2.